Okay, so we've been talking about gases, and we've hit a number of sort of gas laws along the way here um, yesterday, basically. So we started talking about some important units of gases. So obviously, three major sort of units that we come across a lot in most classes is atmospheres, millimeters of mercury, and torr. There are others, as we talked about, there's things like bars and kilopascals and psi and all those type of units. But probably for the most part, in most chemistry classes, these are kind of your three basic sort of units that we come across when we talk about pressures. There's a relationship between them that we talked about, and that's where the 760 comes into play. 760 millimeters of mercury is a atmosphere, and 760 millimeters of torr is also an atmosphere. So 760 is sort of your conversion factor to go between the different units. Remember that a millimeter of mercury and a torr are equal to each other. So it's sort of a one-to-one sort of relationship. Pressure is obviously caused by collisions, as we're talking about gas molecules, which are constantly sort of flying around. As they're flying around, they're making collisions with, the walls of the container and such. And obviously, the increase in the rate of collisions obviously affects the amount of pressure that we see. We talked about sort of three variables when we deal with gases, and that's pressure, volume, and temperature. And we talked about Boyle's law last time. And Boyle's law dealt with the pressure volume relationship. P1 V1 is equal to P2 V2. This would be at constant temperature. And what we see is what we talked about is sort of an inverse relationship. If the pressure is high, the volume is low. So we have a lot of gas molecules in a very small area, going to increase the rate of collisions, going to increase the pressure, and vice versa. The pressure goes down as the volume goes up. And for the same sort of reason, as we increase the volume, we're giving everybody a little bit more room to fly around in. It's going to take longer for collisions to occur, which means less collisions. Less collisions means we see the pressure goes down. In terms of units, we're good on any units in this formula as long as they are the same on both sides. So if you have two pressures, they need to be the same units. If you have two volumes, they need to be the same units. But they really can use any sort of units you like in there. We also then went and talked about Charles' law. Charles' law dealt with volume and temperature relationship. So V1 T1 is equal to V2 T2. This is at constant pressure. So what we saw with this one is at constant pressure, and the way that it's able to really maintain constant pressure is it's the volume, and the volume really does sort of adjust to allow the pressure to remain constant. When we increase the temperature, we're adding more energy to the gas molecules, so they are going to be flying around faster. If we decrease the temperature, they're going to be flying around slower. So when we increase the temperature, we do increase the volume as well. And that basically is because they are flying around faster. So we're going to give them more space to fly around in. By having them more space for them to fly around in, it maintains the pressure and keeps it constant. Opposite is true. If we decrease the temperature, everybody's flying around slower, which, if nothing occurred, we would lead to a lower pressure. So in order to keep the pressure sort of constant, we drop down the volume. That allows the rate of collisions to maintain and also keep the pressure constant. So we see sort of as one goes up, the other goes up, and as one goes down, the other one goes down here. Also really important in this formula and every single sort of gas law formula is the temperature does need to be in Kelvin. So every gas law, pretty much all the temperature values do need to be in Kelvin. Even as we talked about yesterday, if you come across a problem where they, again, give you the temperature in Celsius or something like that, and then asks for the answer in Celsius, you still need to convert it to Kelvin and put it into the gas law in order to do it correctly. We also talked a little bit about in relationship to Charles' law, Guy Lussick's law as well. And that's sort of a similar relationship, which is P1 over T1 is equal to P2 over T2. This is at constant volume. So unlike sort of the previous case there, and again, the temperature does need to be in Kelvin on this one as well, the volume will not adjust as the temperature changes. So what we end up seeing is as we increase the temperature, because they are moving faster, those gas molecules, the rates of collisions increase because the volume is fixed, it's rigid, it's not going to move. So basically they're going to hit the walls of the container a lot more often, going to increase the collisions. That's going to result in an increase in pressure, and vice versa. If we decrease the temperature, again, they will be flying around a lot slower, going to take longer for collisions to occur. And again, because the volume is not adjusting in this case, it's pretty much fixed, we will see that decrease in pressure like we would expect. We also talked about our good friend Avogadro. Avogadro is V1 over N1 is equal to V2 over N2. Here, this is at two conditions, constant temperature and pressure, and N is the moles. And we saw this relationship that basically sort of the volume and the moles are sort of proportional to each other. If we increase the volume, we do see an increase in the number of moles. And that's again a way to keep it at constant pressure. And if we see a decrease in the volume, we see a decrease in the number of moles. Again, a way to keep it at a constant pressure by adjusting the moles sort of proportional to each other as the volume does. Another sort of important relationship that we saw with Avogadro's law is in the aspect of stoichiometry, because there's sort of that relationship between sort of volume and moles. In this situation, we saw that you could do a stoichiometry problem using sort of a volume to volume relationship rather than a mole to mole relationship if you're dealing with gases and you're dealing with constant temperature and pressure in that sort of situation. So I think we did like, 1 liter equals 4 liters or something like that in that example. So we're able to sort of use that as an aspect of Avogadro's law. We also, as we talked about, can just plug and chug into Avogadro's law like any of the other gas molecules or gas laws here. Putting all these together gives us, as we talked about, sort of the ideal gas law. And the ideal gas law is our PV is equal to nRT. Remember that the ideal gas law is a little bit different than all the other ones there that we've just talked about. First major difference is, as we talked about, that it's not like a before and after condition. So there's not two pressures, not two volumes. It's sort of a one situation. The other main thing about sort of the ideal gas law is that it is the most restrictive in terms of units. Everybody needs to be in certain units. So pressure, when you use the ideal gas law, has to be in atmospheres. Volume has to be in liters. Obviously, moles should be moles, and T should be Kelvin. So very restrictive. You got to be in those units. And really the reason why you have to be in those units is because R is a gas constant. And again, it has a value of 0.08206 liters times atmosphere divided by Kelvin times mole. So again, as we talked about last time, those are all the units that we see in the ideal gas law. And that's why everybody else has to be specifically in those units for everything to properly cancel out for it. It's obviously a formula that you could use in sort of a one type situation. It's used a lot to solve for any of these things, really: pressure, volume, R, temperature, even moles sometimes as well. You always have R, even though it's not usually given to you in a lot of problems. So that's something you should always keep in the back of your mind, that you really do have R. We talked about a couple of other things here to close out sort of our gas conversation yesterday, and that was STP. STP stands for standard temperature and pressure. And again, when you are given STP or told it's under STP conditions, you are actually given some values. That means the temperature is 273 Kelvin and the pressure is 1 atmosphere. Now, we saw a specific relationship that can allow you in certain cases not to have to use the ideal gas law, and that is at STP conditions only, 1 mole of any sort of ideal gas is equal to 22.414 liters. So that's a nice little conversion factor that you can sometimes use. We could always use when you're at STP conditions. Again, if you're not at STP conditions, you can't use it, but it will allow you sometimes to sort of bypass using the ideal gas law. As we saw in that example that we did, if you can't remember that or not sure you should use it, you definitely can still just put all the numbers into the ideal gas law and you could solve it the same way and you'll get the same answer. Again, you would just use pressure as 1 atmosphere and temperature would be 273 in a problem like that. We finished up on here, I think, talking about the combined gas law. And that is where we have all 3 variables sort of happening. P1, V1 over T1 is equal to P2, V2 over T2. Again, this really is sort of developed from the ideal gas law where we solve for R. And in most cases, N remains constant as well. So that's why we don't see it here. Same deal with this one. We could do any units we want on the pressure to volume. The temperature does need to be in Kelvin in this case. And again, obviously the temperature needs to be in Kelvin in every case in terms of sort of gas laws there. Yeah, so the question is 22.414 liters at STP only for gases? And the answer is yes, it is. So if your question is about this relationship here, it is only for gases. And it's only for gases under one specific condition, which is STP, which means, as we talked about last time, if the temperature is not 273 and the temperature is not 273 and pressure 1 atmosphere, you can't use it. So it's got to be both of those things. Has to be under STP conditions, and it would only be relatable to gas. Other questions on that? All right, so I think that wraps up pretty much what we talked about last time. Any questions on any of those laws? Again, obviously what's in the boxes, pretty much what's on the slide, you do need to know, obviously. Any questions on any of that stuff we talked about last time there? Okay, then we're going to continue on a few more gas laws type things that we're going to talk about. And again, a number of these sort of laws probably were maybe reviewed to or maybe you've seen before. Maybe some of you haven't. We're going to talk about how to calculate certain things here that maybe be a little bit new to you. So the first thing we're going to talk about is, how to calculate really 2 sort of properties, I guess, of gases. And that is basically the density and the molar mass. So if we want to calculate the density of a gas, there's really a couple of ways you could do it. First off, you could just memorize the formula that we see there. And I'm going to talk to you and just kind of show you, where these guys are sort of come from and where they're derived from. But the density is mass over volume. And remember that when we talk about the density of a gas, as we talked about earlier, typically speaking, the density of gases are given in grams per liter. So that's a very common unit that's given in terms of the density. And that would equal the pressure times the molar mass, which is what the big M is, divided by RT. And we would sort of use that formula to calculate the density of a gas. You could also calculate the molar mass of a gas. The molar mass of a gas or molar mass of anything is in units of grams per mole. And the molar mass would equal the density in grams per liter times R times T divided by P. So really all of these guys are really uh, basically derived from the ideal gas law. You could actually use the ideal gas law instead of sort of these formulas. They're really the same, but if you don't want to memorize these, you can kind of use the ideal gas law, and we'll talk about kind of how to do that here in just a second. So why don't we try one here? Actually, yeah, why don't we try this one here and see what you come up with, and then we'll talk about another way that you could solve it if you can't remember that formula, and why what we just saw is sort of based off of the ideal gas law. Okay, let's take a look here and see it. So again, you could definitely, since we're going for the molar mass, which is in grams per mole, you could use the formula that we just saw sort of over here, which is the density times RT divided by P. And, you could plug all those things in. When you do so, again, if we just look at the units there, grams per liter for the density, we have our liters, atmosphere, Kelvin, mole. For our R, we have our Kelvin, and we're dividing by our atmospheres. So here again, if you just cancel out the units, liters cancel, Kelvin cancel, atmospheres cancel, we're left with the units of molar mass, which are grams per mole, which is essentially what we're looking for. Now, if you can't remember sort of that equation, or you're not sure, you really can approach this more as a sort of conversion factor, conversion type problem, and you could use really the ideal gas law to help you out. So if we think about sort of the information given to us, let's just kind of pull out the information. We do have the volume. The volume is 2.1 liters. We have 4.65 grams. We'll leave that off for just a second. We have a pressure that is 1 atmosphere, and we have a temperature that is 27 degrees Celsius. Remember that we are looking for ultimately grams per mole, which is the molar mass, and that grams part is actually given to us. So that's actually the top number right there. And you don't have to really do much with that number. You can basically just plug it right into your grams per mole. That means ultimately what we're missing in terms of solving this, if we're not going to just kind of plug it into the formula before, is moles. So we're kind of missing moles. So if you put that with everything else that you have, you could kind of see the ideal gas law, which again is really where these formulas come from. If we look at the ideal gas law, we do have the pressure given to us, we do have the volume given to us, we do have temperature given to us, and we always have R. So we can actually just use the ideal gas law here to solve for N, and N would be PV divided by RT. And again, that N would actually be the moles part that we need. So the formulas that we saw on the previous page really are rooted in the ideal gas law. Here you can see you can kind of use the ideal gas law and just kind of think of it like a conversion type problem. And you could get to the same answer you would get when you would put it in there. If we did that, that would give us 1 atmosphere for our pressure. Our volume was 2.10 liters. Our R was 0.08206 liters atmosphere Kelvin mole. And we've got their temperature, which obviously does need to be converted into Kelvin there. So I think that's 300 we got going on there. That means the mole part that we get is 1 times 2.1 divided by R and divided by 300 gets us 0.0853 moles, which again is the bottom part. Now we have really everything we need to solve for the molar mass there. It would be 4.65 grams divided by 0.0853 moles. Again, here the units do not cancel out, which is good because the units of molar mass is grams per mole, gives us something like 54.5 grams per mole. Any questions on sort of any of those steps? And again, you should really get pretty much the same answer there if you plug it in. You would take the grams and divide it by the liters to get the density. You would then times it by the gas constant, times it by the temperature there, and then obviously divide it by our pressure. And you should get the sort of same answer there. And you do. So again, you could go right into the formula, or again, if you can't remember it, you can always use the ideal gas law. So you can really, for both of these sort of formulas here, they're both really based off of PV equals nRT. And that's sort of how you can kind of get to sort of each of these here as well. Any questions on that particular problem there? Why don't we try another one here? Why don't we do... let's do, what is the density in grams per liter of N2 at 27 degrees Celsius and 1.25 atmospheres. I think that might be all that you need as well. Obviously, nitrogen is 1401. All right, so take a minute or two and see what you come up with. All right, let's take a look at this. Again, you do have two options. If you memorize sort of the formula there, you can definitely punch it into this guy here. And again, if we look at units, pressure would be atmospheres, molar mass would be grams per mole. R, again, our liters, atmosphere, Kelvin and mole. And our temperature in Kelvin. Kelvins would cancel, moles would cancel, atmospheres would cancel. You got grams on top, liters on the bottom. Gives us our units of grams per liter, which is, really what we're shooting for here in terms of density. Again, in this situation, if you really couldn't remember that formula, the ideal gas law is, again, a good thing to sort of think about, and really what that sort of guy is based off of. So if we think about sort of the information that we have given to us, we do have the temperature, which is 27 degrees Celsius. So obviously we need to convert there. And that gives us 300 Kelvin in this particular case. We also have a pressure given to us, which is 1.25 atmospheres. So if you just think about what we got going on here, we have pressure given to us, we have temperature given to us, we always have R. We don't have N or V. So you can, in this case, rearrange the ideal gas law to solve for N divided by V. And if you do that, you basically can take V to this side and RT to the other side. That gives you the P over RT. And by the way, that should look pretty familiar because that is part of this formula right here. As you can see, that is the P and the RT part of it, right? And that really does come from the ideal gas law. By the way, when we do this, we know that N is moles and V is liters. That is the moles per liter. That really is the, should we go this way? That's the molarity, right? So you actually can solve for the molarity of a gas by taking N over V and solving it this way. We could do that again because we do have that information. So if we put those numbers in, that gives us 1.25 atmospheres. That gives us our 0.08206 liters, atmosphere, Kelvin, and mole. And that obviously gives us our 300 Kelvin in that particular case. And if we do that, we end up with 1.25 divided by 0.08206 divided by 300. And I'll just come over here. That gives us 0.05078. The units at this point, if we look at it, we got atmospheres cancel, we got Kelvin that cancel. We have liters per mole, which is on the bottom. So when you divide it, it flips over and becomes what we expect it to be, moles per liter. So if we think about our sort of density, we're almost there. We got liters correct, but we do need to convert it into grams. So at this point, it really is just a conversion factor. How do we go from sort of moles to grams? We use the molar mass to do that. So we would need the molar mass of N2, which is really what this is right here, molar mass. So N2 would be 2 times 1401 grams per mole. And basically, that's going to give us 2802. Come here. There we go. 28.02 grams per mole. And we could really just do a conversion at this point, get rid of the moles. So on the bottom would go moles, on top would go our molar mass. Moles would cancel, and now we will be left with our 1.42 grams per liter as our density. So you can see really they are both rooted in the ideal gas law, and it's basically what we just did. We used the ideal gas law for the highlighted part, times it by the molar mass, right, which is what we did here. So if you can't remember these guys and you're asked to solve for something like density or molar mass, you could really a lot of times just kind of approach it as a conversion problem and think about the ideal gas law as sort of your guide that will allow you to kind of do that conversion, and then you'll be left with really some type of conversion at the end of it, and just try to get the units into the right spot. Any questions on density or molar mass? Okay. So the next thing we're going to talk about then is stoichiometry that involves gases. And obviously stoichiometry that involves gases pretty much works the same way as regular stoichiometry. Looks like my arrow missed there, so we'll kind of fix that a little bit. So really you do follow those same sort of 4 steps that we've talked about before. The difference is, though, somewhere along the way in the calculation, you're going to use the ideal gas law. You may even use it twice, PV equals nRT. So somewhere along the way, you'll use it. Either you'll use it up front, kind of like on the second step where we get to moles. So that second step in a stoichiometry problem is convert what they gave you into moles. Then if you use this sort of up front, you typically would be solving for N. If you use it sort of on the back end of the calculation, which is typically step number 4 for us, you most likely will be solving for volume, because you will have moles at that point, and you usually will solve for volume. So those are 2 places sort of where you would sort of typically use the ideal gas law. Everything else is pretty much the same. We still need a balanced equation like normal. We still need to convert to moles. We still need to do the mole-to-mole relationship. And obviously, we still need to convert those moles into whatever unit they're looking for. So here we're looking for what is the volume of CO2 that's produced at 37 degrees Celsius and 1 atmosphere when 5 grams of glucose are used up in a reaction. So here we're going to sort of do a stoichiometry problem. And if we look at some of the information here, let's see what we got going. There it is. First off, we do want to balance the equation. So we do have an equation here. It is balanced. We're given some information. We are looking for the volume of CO2. CO2 is a gas, so we're looking for the volume of it. We have a temperature that's given to us, which is 37 degrees Celsius. We also have a pressure that's given to us, which is 1 atmosphere. And we got 5.6 grams of glucose, which is not a gas. And that's a C6H12O6. So this is really all the gas sort of information. And if we think about it, we are going to want to end there. So we are going to kind of come over here and think about the ideal gas law probably at the end. And that is where we are looking for volume. We have the pressure given to us. We have the temperature given to us. We always have R given to us. So we are missing N, which is the moles of the CO2. And the moles of the CO2 are going to come from the stoichiometry part of it. And since we already sort of accounted for all this stuff, the only way to get to moles of CO2 is to really do our stoichiometry starting with this guy here. So the first thing we want to do is really the second step, which is convert to moles. And this part will be just like we've done in the past, since we are starting with grams here. So 5.6 grams of our C6H12O6. Obviously, to convert to moles there, we do need the molar mass of it. So that is 6 times 12.01 for the carbons, plus 12 times 1.008 for the hydrogen, and 6 times 16 there for the oxygen. That gives us a molar mass of 180.2, we'll call it. You get that? So we're going to divide by that number, 180.2 grams per mole from the periodic table. That will get us 5.6 divided by that. Gets us something like 0.0311 moles of C6H12O6. Again, we did get into moles, and it's important to remember that that is moles of the glucose in this case, and we're not interested in the glucose in this case, but we are interested in the CO2, and that is where the stoichiometry is going to come into play. From the equation, we can see that for every 1 mole of glucose, we get 6 moles of CO2. So that is really the third step, like we would do in our traditional stoichiometry problem, 0.0311 moles of our glucose. From the equation, we see we have a 6 moles of CO2 to 1 mole of our glucose. That gets us times that by 6.1865, we'll call it 0.1865 moles of CO2. Now we have the moles of CO2 that we need. And remember, because we're dealing with CO2, we want to make sure that we are using the correct moles. Now we do have everything that we need to get to the volume of the CO2 that would be produced, which is a common question. So number 4 here is very typical in a sort of gas stoichiometry problem. On the back end here, we are going to use PV equals nRT to convert those moles into some other unit. In this case, it would be volume. So the volume would be nRT over P. We have each of those numbers. So N is our 0.1865. Our R is our 0.08206. Our temperature, it is still the ideal gas law, so we do need to add a 273 to that to make sure that everything cancels out correctly. Looks like a 310. All that being divided by our pressure, which was 1 atmosphere. In terms of units, atmospheres cancel, Kelvin cancel, moles cancel, leaves us with liters, which is good because we're looking for a volume. So that's going to be 0.1865 times 0.08206 times that by 310, looking like we're going to end up with approximately 4.74 liters of CO2 would be produced. That would be, by the way, the theoretical yield of CO2 in this reaction, based off of the equation. Hopefully you can see it really is the same sort of stoichiometry steps. Again, we just kind of really use the ideal gas law here at the end, which is a very, very common sort of procedure. And as I mentioned before, you could potentially use it in step number 2, where you would be solving for moles. Any questions on that there? Okay. And a reminder as well that, and with any sort of stoichiometry problem, we do want to make sure that it's not a limiting reagent problem. And again, here we knew it was definitely not a limiting reagent problem because we weren't given any information about both reactants, right? So that's the product. So we really didn't have information about this guy. And we were only given information about this guy. So again, it's a basic stoichiometry problem. You could absolutely, like we've seen in the past, have a sort of limiting reagent problem, and it would be worked the same way, obviously, as what we've done before. All right, why don't you give one a go here and see what you come up with. Let's see here, maybe. Magnesium reacts with hydrochloric acid, maybe. The rest of it will come. There it is. Perfect. Magnesium reacts with hydrochloric acid and hydrogen gas is produced. According to that reaction there, or that equation, calculate the volume of hydrogen gas produced at STP by reacting 5 grams of magnesium with excess amount of HCl. So I think perhaps the only thing you might need is magnesium's molar mass there is 24.31 grams per mole. All right, take a few minutes and see what you come up with on this one. Okay, let's take a look and see how we're doing. So obviously it's a stoichiometry problem, got an equation, got some information given to us. So we are looking for the volume of hydrogen gas. So for hydrogen, which obviously is a gas. So we're looking for the volume of it at STP. Remember, STP is standard temperature and pressure. That means that the temperature is 273 Kelvin. The pressure there is 1 atmosphere as well. And we always have R, if you're thinking about sort of the ideal gas law, which we should be thinking about sort of in a stoichiometry sort of situation, because that's usually the only gas law that you kind of use when you're kind of doing it. So we just think about our PV equals nRT. We obviously are looking for the volume. We do have the temperature given to us. We do have the pressure given to us. We do have R. So much like what we saw in the previous problem, kind of the only thing we're missing for H2 to sort of help us solve it is the moles. And if we think about that, the only leftover piece of information that we sort of have in this problem is the 5 grams of magnesium, which is obviously not a gas, so we can't do anything with it in terms of the gas law, but we can do something with it in terms of stoichiometry by using stoichiometry to go from magnesium to the hydrogen. So that's where we really want to start. So we have our equation. It does look balanced. Yes, it does. We then want to convert into moles. So in this case, we have our 5 grams of magnesium. We would go to the periodic table there and see it's 24.31 grams per mole. That is going to get us 5 divided by 24.31. Gets us something in the ballpark of 0.206 moles of magnesium. Again, though we do have moles, it is not the moles that we need. We do need, obviously, the moles of hydrogen gas. So that really is where the stoichiometry comes into play. We can then look at the equation. We see that for every 1 mole of magnesium, we get 1 mole of H2. So that makes this calculation relatively easy. 0.206 moles of magnesium. Again, doing our mole to mole relationship from the equation, 1 mole to 1 mole gives us 0.206 moles of H2. Now we do have the correct moles that we're looking for, so no longer missing 0.206. And now we can go into the 4th step, which again, instead of sort of using the molar mass to convert to grams, we're going to actually use the ideal gas law here. And we're going to once again solve for V, which would be nRT divided by P. Putting in our numbers, 0.206 moles of H2 are 0.08206. Our temperature, which is 273 because it's STP, and our pressure, which is obviously 1 because it's STP. Everybody's going to cancel out except for our liters. There's our liters left over there, and that gets us approximately 4.61 liters, give or take. H2 would produce. Again, this would be your really theoretical yield of H2. Any question on any of those sort of steps there? Now, we could have sort of solved it a little bit different as well. And again, just to show you an alternative sort of way that you could have done this guy. And it is because, again, we were at STP. And remember that at STP, 1 mole of any gas is the 22.414 liters that we were talking about earlier. That means that we could have, at this point, kind of picked it up, not used the ideal gas law, and went 0.206 moles. A mole is 22.414 liters. And we would end up with, hopefully, with rounding, probably about the same, about 4.61 liters of H2. Maybe 4.62 if you round it a little bit, but pretty much the exact same answer. So again, you do have an option in this case because it was STP. And this is what I was talking about earlier, where I said, in this situation with the STP, you can avoid, obviously, the ideal gas law number 4 by just using that conversion factor. But again, a reminder, only can be used in STP conditions. Any questions on that one there? Our stoichiometry in general. All right, so we talked about stoichiometry. The next thing we're going to talk about is partial pressures and Dalton's law of partial pressures. And sounds very sort of difficult, if you will, but it's not as hard necessarily as you may think. So, for example, if we look at these different sort of situations here, in sort of the first container, we have, I guess, reddish gas molecules flying around. So we got some red gas molecules basically flying around. And when we think about sort of the pressure associated here, basically the total pressure that we see in this particular container is really all from the red sort of gas molecules, or P1 we'll talk about. So its contribution is basically all from those red gas molecules as they're flying around, they're hitting the container. If we look over here, we've got some green gas molecules, and those guys are also the only gas molecules that's in that particular container. That means that the total pressure here would be a result of their pressure as they're flying around. But very often, though, gases are basically found as a mixture of different gases. Now, if we put sort of our red guys together with our green gas molecules in the third container, now both of those gases are contributing to the overall pressure of that system. And in this case, the total pressure would be a result of P1 plus P2 in this particular case. And they are both barely contributing to the pressure. What we would call these pressures in this particular case, P1 and P2, as I missed it, let me just move that arrow that way, and P2, they would be referred to as partial pressures. So what does partial pressures really mean? They mean that they are partially contributing to the overall pressure of the container. So how do we get the partial pressures? Well, for the most part, in a lot of sort of partial pressure type problems, we actually just use the ideal gas law. And the ideal gas law, again, is PV equals nRT. Now let's think about sort of this situation that we see here in this container. What we see in this container is this container has the same volume for every gas, because we look at the volume of the container. And that container is most likely sitting on the same counter. And that would then mean it has the same temperature for each of the gases that are present. So typically speaking, what we do is we would take the ideal gas law, we would solve for P, and we would solve for P for each of the gases individually. And the temperature for each gas would be the same. The volume for each gas would be the same. R as a constant would be the same, which means in most cases, the only difference that you need to sort of worry about is how many moles of each of the individual gases do I have. Again, you would put it into the ideal gas law for each gas separately. You would then get the partial pressures, and then you would simply add them together to get the total pressure that's happening in that mixture. Any questions on that there? This is one of the things, as we'll talk about here in a second as well, but we kind of touched upon it the other day. This is one of the ideas that makes something a ideal gas law, or sort of the reason we could do this type of calculation is, again, under sort of the ideal conditions, we assume that even though there's multiple gases sort of flying around in the same container, there's kind of no attractive forces, repulsion forces. They're really not going to interact with each other. So you could almost think of each gas as being in that container by themselves, even though they're not, because the other one really will not influence anything in terms of the other gases that are flying around. So although there's multiple gases flying around, in this sort of ideal situation, we could think of them as kind of being in there by themselves. And that's why we could do these type of calculations to figure out the partial pressures and then obviously the total pressures. So that's a very common way that you can sort of solve for the partial pressures, is by, again, taking really the ideal gas law, solving for each gas individually, and then adding them together as we sort of see in this situation. Now, there can come a time where you may not be given enough information to actually use the ideal gas law. So maybe you're not given, volumes or temperatures or pressures or those type of things. So maybe you're lacking enough information in a partial pressure situation to actually calculate the pressures using the ideal gas law. But if you are given enough information to figure out the moles of the gases that are present, so maybe you're given the grams of each gas, or maybe you're just straight out given the moles of each gas. If you're able to given the moles of each gas, and you're given one other piece of information, either the partial pressure of a gas or the total pressure of the mixture, you are able to use this formula on the bottom here to actually calculate the partial pressure of a gas by using this one here. This is the partial pressure of whatever gas you're looking at. This is our total pressure. And X is what we saw earlier. X is our mole fraction. So if you remember, our mole fraction is the moles you're interested in divided by the total moles, again, without the multiplying by 100. So this allows you a nice little sort of option if you're not given really enough information to use the ideal gas law. But again, what you would need to be given is enough information about getting the moles of each gas, and also something about some type of pressure, either a partial pressure given to you one of them or a total pressure. And you can use actually the guy on the bottom there and actually solve for the total pressure and the partial pressures and all that kind of stuff. Any question on those two sort of ways? All right, so let's take a look at an example here and see what you come up with. So why don't you give this a go? We got 5 grams of helium. We got 5 grams of neon. We threw them in the same container at 2.5 liters at 27 degrees Celsius. What is the partial pressures of each gas, and what is the total pressure? So we're looking for 3 answers here: 2 partial pressures for helium and neon, and the total pressure. So take a few minutes to see what you come up with. Helium is 4.003 grams per mole, and neon is 2018 grams per mole. All right, so take a moment here and see what you come up with. Okay, let's see how we're doing here. So let's take a look here. So we are having a sample here again that basically has helium floating around in there. It's got some neon floating around in there, obviously in the same container. We'll put a lid on it so that it won't leave. So we do have some information given to us. Obviously, we have the masses of both helium and neon given to us. We obviously do have a volume here of 2.5 liters. We have a temperature of 27 degrees Celsius, which obviously we do most likely need to convert to Kelvin. So we'll call that 300 Kelvin at that point. We are looking for the pressure, obviously, for each of the gases. And obviously, we always have R. So again, here, the ideal gas law is probably a pretty good route here to solve it. There you go. So if we use PV equals nRT and just sort of cross off what we got going, we do have the volume, we do have R, we do have T. We are going to need to figure out N, or the moles of each gas, which we definitely could do since we have the grams. So we really could solve this for P is equal to nRT over V. Again, before we could do that, obviously we're missing the moles of each gas, so that's where we want to start. So the moles of helium would be 5 grams of helium using the molar mass from the periodic table, 4.003 grams per mole. That does give us 5 divided by 4.003. There we go. 1.25 moles of helium. We could do the same thing for our neon. So we got 5 grams of neon using the molar mass from the periodic table there. 2018 gives us for our neon. Looks like 0.248. So really that does now allow us to have the moles for each of the gases. So we're going to simply, as we talked about previously, just going to do 2 separate calculations for each gas. So the first thing we're going to do is we'll do it for helium. And again, it would be nRT over V. So our N for helium was 1.25. Our R is 0.08206. Our T, which is 300 Kelvin, all divided by our V, which is 2.5 liters. And if we do that, we end up with 1.25 times 0.08206. 300 divided by 250. Looks like a 12.3 atmospheres. We could do the exact same calculation for neon. Really, the only difference is going to be here in the moles part. We want to make sure we use the moles of our neon in this case. But because they are in the same container, pretty much everything else is going to be identical in this calculation. All divided by our 2.5 liters. And that's going to get us 2.44 atmospheres. First off, any questions on these 2 calculations here? These 2 numbers represent, just so we're clear, the 12.3 represents the partial pressure of helium. The 2.44 represents the partial pressure of neon. So the last thing that we're interested in is what is the total pressure? Remember that the total pressure really is just adding up all of the partial pressures, which means in this case, the partial pressure of helium plus the partial pressure of neon, which means we would take our 12.3 plus our 2.44, and that gives us a 14.7 atmospheres as the total pressure of this particular container. Any questions on any of those things? We could also see from these calculations that the major contributor here in terms of pressure is helium. Helium is contributing 12.3 atmospheres of the pressure. Neon is only contributing 2.44 atmospheres. And we will answer the question of why that is in a few slides down the road here in this lecture, but we'll answer why that happens as well. Any questions on that calculation there? Okay. So why don't we try this partial pressure type problem? A sample gas contains 8.24 moles of methane, 0.421 moles of ethane, and 0.116 moles of propane, which is the C3H8. If the total pressure of the gases is 1.37 atmospheres, what is the partial pressure of propane in this case? So take a couple minutes, see what you come up with. Yeah, let's take a look at this one. So obviously we're doing something with partial pressures. So we may think about the ideal gas law here, PV equals nRT. In this case, we're given the moles of 3 different gases, which are obviously floating around in there. So we do have moles. We always have R. And that's sort of all we're given. We're missing volume. We're missing temperature. So the ideal gas law is really probably not going to be too helpful in this particular case. But since we do have moles and we do have the total pressure given to us, which in this case is 1.37 atmospheres, we can use that other equation that we saw, which was Pi is equal to Xi times Pt. Again, Pt is the total pressure. Xi is the mole fraction of the gas you're interested in, and Pi is our partial pressure. So we can definitely use this formula to help us determine, in this case, the partial pressure of, looks like propane. So remember, in order to calculate the mole fraction, we do need to get the total moles that are going on here. So our total moles of our gases are 8.24 plus 0.421 and 0.116 moles. That gives us a total moles of 8.24, 0.421, and 0.116. Looks like 8.777 moles. So remember, the mole fraction is basically the moles of the gas you're interested in divided by the total moles. Again, not multiplying by 100. So in this case, we're interested in propane, which is the C3H8. And in that case, the moles of the propane is 0.116 divided by the total moles, 8.777. That gives us a mole fraction of, looks like 0.0132. And again, that is the mole fraction. We do have the total pressure, which means we now can solve for the partial pressure of propane by simply taking 0.0132, which is basically 1% of our total pressure, which was 1.37 atmospheres. And that obviously does give us 0.0132 times 1.37. And maybe if I hit the right button there, that might work better. Try that. 0.0181 looks like. 0.0181 atmospheres would be our partial pressure of our propane. You obviously could do it for every gas that's here. You know, you could have done it for your ethane. by simply taking the moles of your ethane, which was 0.421, divided by 8.777, and you get the mole fraction of your other guy, which is about 4%, 5%, I guess, 0.480. And obviously you could do the partial pressure of your ethane in that case would be 0.0480 times 1.37. And that would get us 0.0658 atmospheres is the partial pressure of ethane. You could do one of two things for the last one. You could either add both of those pressures together and subtract it from 1.37, or you could do the mole fraction and multiply it. Any questions on this type of partial pressure type problem? So far we've seen sort of two partial pressure type situations. One where you can use sort of the ideal gas law to basically solve for pressure in each case, add them together. We see one like here as well, where you could, if you don't have enough information to get yourself in the ideal gas law, but you do have enough information about moles and such, you can figure out the partial pressures. A third type of sort of partial pressure situation that occurs a lot of times in the laboratory when you're doing an experiment. And in an experiment, a lot of times what we'll do is we will sort of collect the gas in a sort of water situation. So for example, here we have some potassium chlorate and some MnO2, going to heat it up. We start out with a kind of glass here just fully filled with water, kind of covered. It's then dumped upside down in this bucket of water over here in this trough, basically. We put sort of the tube into the water container. When this started, this thing was completely filled to the top and bottom there with water, no air or anything in there. And as we start to heat this is going to actually generate some oxygen gas, some O2 gas. And obviously in this sort of closed situation, the oxygen gas has nowhere to go. And it basically will continue through the tube here. We stay in the tube and obviously start to bubble in. As the oxygen gas goes in, the water goes out. And basically we're displacing the water in that container, which again started over here completely full with basically oxygen gas. And you'll continue this reaction till it's over. And at some point you'll have this spot over here in the container that looks empty, but it's really not empty. That is again where all of your oxygen gas basically came. That's basically where your O2 gas ended up. But in this situation though, because we did it with water involved and collecting the gas in this water environment, when we do this reaction, there's got to be probably some type of heat or something that's going on. And what typically will happen in this situation is, in addition to collecting the oxygen, you're going to also collect some water vapor in there as well. So you're going to have some water vapor that has been collected as well. So we're really interested in the oxygen here, but in this situation, we just created really a partial pressure situation where we have multiple gases that we collected. That means when you go to get the pressure here, the total pressure, we actually do have a mixture of gases. We have the pressure of the gas that we're interested in, like the oxygen, plus the pressure of the water vapor. And this is what is known as the vapor pressure of water. That is actually a value that you find in a table. So that's a value that you look up in a table based on temperature, and it'll tell you, hey, the vapor pressure of water is this at that temperature. In most cases, we are definitely not interested in the water. We really want just the oxygen gas, right? So we don't really want to be concerned with the water vapor. We're interested in this particular example in terms of the oxygen gas. So what we end up having here in this sort of partial pressure situation is we have the total pressure, which, by the way, if you were in the lab, you would take the barometer reading. That would give you your total pressure. We could use this and rearrange it and solve for the partial pressure of the gas would equal the total pressure, which is sort of the barometer reading, minus the vapor pressure of water. So we sometimes have to do this little subtraction here to correct for the vapor pressure of water. And this will sometimes give us what is referred to occasionally as the pressure of the dry gas, because we have now just taken out the water sort of component to it. Sometimes people refer to it, a lot of times in labs, they'll refer to it, what is the pressure of the dry gas? And that's sort of, why they say that, because you're kind of subtracting off the water contribution. So this occurs a lot when we sort of collect water and collect gases in this situation. A couple of terminology that you sometimes hear in these problems is collected over water, collected with water vapor, saturated with water vapor. Something like that means that you essentially need to do this subtraction and correct for the water is typically what we see. And here is a table, not the one from your book, but you have a similar one. And again, you can look it up based on temperature, and these would be your vapor pressure water that we would sort of use as a correction value. So if we look at an example such as this that involves something like this, we have a sample of oxygen gas that's saturated with water vapor at 30 degrees Celsius. The total pressure is 753 torr. The vapor pressure of water at 30 degrees is 31.824. What is the partial pressure of the oxygen gas? So the key word here is, as we see here, saturated with water vapor. That tells us that we basically need to do that subtraction correction where we take the pressure of the gas plus the pressure of the water vapor. In this particular case, they were nice enough to give us the vapor pressure of water, which is 30, and they also gave us the total pressure. So we can rearrange this, and basically the total pressure in this case is the pressure of the oxygen plus the pressure of the water. Pressure of the oxygen gas is equal to the total pressure minus the vapor pressure of water, which they gave us was 753 was our total pressure. Vapor pressure of water, which would be found by looking it up in the table, 31.824 torr, gives us roughly, looks like maybe we'll call it 721 torr. It does want it in atmospheres, so we do need to do a little conversion here. 721 torr. Remember, 760 is our conversion factor. So we'll divide that by 760, and it looks like that we end up with 0.949 atmospheres of O2. And again, that would be sometimes referred to a lot of times in the laboratories as the pressure of the dry gas. So again, because we got rid of the water component, basically. Question on that sort of third type of partial pressure situations. So there's really kind of three types of situations or sort of calculations that you very commonly come across. Again, as we talked about, using the ideal gas law, using sort of the mole fraction, or in a case like this where the gas was collected over water or water was involved, you typically need to subtract off the vapor pressure of water and get sort of the pressure of the dry gas, like in the case here. Any questions on partial pressures or anything we talked about here today? Okay, we will lay it up then here.